会 cover 到就是 control analysis 那一段的，就后面的 HMM 这一段，就是不会在这次考试，会在后面这个 final exam 上面出现。那到时候 TA 会再跟大家讲考试的一些规则，基本上扣除可以带大抄这样子。然后TA 会再做个简单 review，然后是这一段嘛，OK，好。Right, so let's continue to Sahita Markov model. We'll do a recap on Sahita Markov model and then try to start into the in-depth of the three basic questions that we can ask about Hidden. Right, okay, so why we talk about Hidden Markov model is because the idea of doing automatic spatial recognition system from a statistical data-driven approach, right? So we kind of already know this, right? Thinking a speech signal that comes in. Like also we do a front end parameterization, we call them features. Okay, so features are things we know that basically do the MFCCs and so on, right? So for each of the basic distinct sounding unit, we can build a Hidden Markov model to understand the acoustic model, acoustic characteristics of that model, of that sound. Okay. And then another thing we'll talk about later is language model, basically how we actually string together letters again probabilistically. Okay, so everything is purely from a data-driven statistical approach. So we know Gaussian mixture model, Hidden Markov model is the basic building blocks for building an acoustic model for each of the sounding units within a particular language, so that we can start building a SR system. For this Gaussian mixture model, Hidden Markov model is we call it parameterized random process model. Okay, so when we call parameterized, always means that whole process, that whole functions are being described by a set of finite set of parameters. So at learning, what you need to do is actually just estimate the values of those parameters from the data, and then you are able to perform recognition. Okay. For the Gaussian mixture model HMM, it actually has this set of parameters. I index the number of states, so the initial state probability vectors, the transition matrix. Okay, it talks about the transitional probability between each of the I to the J state. CJK under so for each of the particular state, for that K mixture, what's the weight of the K mixture out of the Gaussian mixture model as a CJK, right? NJK for each of the state, for each of the K mixtures, what's the mean vector, right? Each of the state, each of the K mixture, what's the covariance matrix? So these three are Gaussian mixture model parameters. You just need to have one set of parameters for each of the state. Okay, the transition across time are basically parameterized by the transition probability across AIJ matrix. The system starts, so you have initial state probability. Okay, so these are a set of parameters that describe the entire GMM HMM random process. Okay, in a parameterized manner. Okay, so we use this set of parameters to fully describe how each sound unit R has an acoustic model. We model that as a Hidden Markov model. We get all the R's, all the E's, all the U's, all the 40 sets of phonemes, and we each one then build a model using this set of parameters describing each of the phonemes. That's kind of the basic ideas behind acoustic model using HMM GMM. Okay, so we'll come back to HMM. So HMM basically think about this transition or this kind of problem. This transition between states happening according to a clock rate. So it's discrete time process. Okay? So it's not continuous time process, discrete time. So when the state transition occurs, imagine every clock ticks, every clock period, whatever they define. In terms of acoustic model, that's basically the step it takes to generate MFCC features, right? That basically that step size is a one clock tip. The model will emit generates output of new data in terms of speech acoustic vector, right? So you imagine there's a HMM GMM system. These are parameterized random process. Every time it ticks, okay, it generate according to some probability a feature that you can observe. Okay, and that feature we usually means the acoustic features, and in this case the MFCCs. Okay, greater some probability associated with that state. So we call this kind of HMM model. Is it a generative model? Okay, so means it's a doubly stochastic. Okay, stochastic basically means probabilistic. Doubly means cross type, cross spatial, cross feature values. Okay, both of them are probabilistics. So state transition probability attempts to capture the durational variability in speech is stochastic, right? That transition probability tells you, okay, what's the probability that you stay in one state or transition to the next state. So those basically help us implicitly model the duration variability of probability, so-called emission probability. You try to model the spectral variability in speech, that's also stochastic. So both of these things are varied. So again, repeat, imagine in your mind, I will always sound. That sound make a frame, that feature of that acoustic value, the feature value of that MMCC will not be the same for every R you look at. So there's some probabilistic stochastic version of that. So that's called spectral variability. Every R that you speak, okay, there's a durational differences. Okay, when you speak really fast, it's less than 100 milliseconds. When you speak really slow, maybe that R will become over maybe 150 or 125 milliseconds. Okay? So there's a durational differences in the R's and the spectral variability differences in the R. So we need a model that handles both this variability using probability, okay, using those parameters that we just designed to be able to handle at random and kind of a guessing, okay, what's the likelihood that these things are being generated from this particular sounding R, or what's the probability that these features are being generated from the other acoustic model called E. Okay, so basically when you look at these model parameters, you can compute, you can score against these kind of models and try to do recognition. Okay, so keep this in mind. So for more basics of LHMM, I think we talk also about this. This try to model the acoustic model probability of observation given a model, and usually this model, this lambda means each of the class. Okay. In terms of speech, it's basically a set of a phonic or distinct sounding unit that whatever you model this on. Okay. O is usually a sequence of observation. HMN is coming from what we call discrete time Markov process. Okay, so you have a dynamical system, it's discrete time and in time instance. The system will be in one of the n state, okay, 1 all the way up to n. At a clock tick, okay, imagine once the system undergoes a state change, it can go from nt to nt plus 1. T denotes the time with a certain probability. Okay, we can denote the state variable as q sub t, right? State variable at the time t. And now we do a drastic simplified assumption on this random system by saying the system is a first order Markov process. Okay, basically, when your system at t plus 1 is in the state j, at t plus 1, the state variable is in j. In addition on all the past histories, okay, the system has been in I, has been J, has been G, and so on and so forth. Okay, we simplify this conditional probability all the way down to just one time step before. Okay, that's called first order Markov process. So probability of Qt plus 1 now is in state J, only depends on the probability of Qt is I, where the previous time point you're in I. Okay, nothing else, and we call this probability Aij. Okay, this is the state transition probability. So we simplify this entire sort of a random sequence generation process by saying, okay, whatever state that you're in, only the probability of getting here, okay, you're in this state, only condition will be only conditioned on the probability that you were in a particular state previous time point. First order Markov assumption, trying to simplify many of the calculations. Okay, we call that Aij transition probability. This Aij is time independent. Okay, that means it's static value. Okay, whatever t is, t equals 1, t equals 5, t equals 100, t equals 5,000, they are the same Aij. So that means every state transition, that probability doesn't change. Okay, there is a probability, so there is an uncertainty, but that uncertainty is not changed. Okay, so that's what it is. So we always assume in a hidden Markov model, since the Aij is independent. Okay, so that indicates the process of going from I to J. And we know according to laws of probability, right, this probability Aij has a gradient equal to 0, okay, because it's just a conditional probability. Okay, some over all possible ways, right? J's going from I state to J, going from for all I or sum from J from 1 to n, Aij has 1. Basically, the total probability needs to sum to 1. Okay, going real quick through this, we'll talk about this, right? What's the probability, under this kind of dynamical system, first order Markov process, okay? What's the probability that state at t plus 1, right? Qt plus 1 equals j, right? Qt can be in any of the states, right? So, could have the end of state such that Qt equals to I for all I equals to 1 to n, right? So, okay. So what we need is, right, the next time point, right, t plus 1, you're in state j, okay, j can be reached from one of the n states, right? So you could reach from one of the I from 1 to n, right? So in the previous time, you could be in 1, could be 2, all the way up to n. When you're in 1, you move to j, right? So the probability that your previous time point is in I, multiplied by the probability you're going from I to j, somehow all the possible ways you can go from the previous state to the current state of j. That's the total probability that you are in j state, right? So P of Qt equals to j. You sum up all the possible manners it actually reaches to the point of j state, okay, across all n different states. You can write it as matrix form, then you look something like this. So those things we call transition probability going from state 1 to n. Question 2, okay, how to calculate the state sequence probability? For example, what's the probability of this particular sequence? The first stage is I, the second stage is J, the third stage is K. So you need an initial state probability. Okay, so let's assume P of the initial state probability equals I, so pi I is just the parameters. So now you have this sequence, right? P of Q1 equals I, P of Q2 equals J, P of Q3 equals K, right? This is a joint probability of a particular sequence. Okay, when you look at the joint probability, then you can actually factor that. Okay, because of the first order Markov process that we assume. You have the initial state, you're actually going from I to J, and then you further go from J to K. So basically, you break this joint distribution into a series of conditional probability that's only depending on one previous time point. Okay, so the first order Markov assumptions. Okay, so now we can generally we can write the probability at a particular time t you're in m state basically equals to, right, initially you can go from 1 to your initially can be from 1 to n state, right, going from any one of those I to j, then sum over all possible j, all the j's goes to k, sum over all to the point L, m, so all of the L, okay, in the previous time index range from 1 to n going to the m state. Okay, that's the probability that eventually at time t you're in m state. Again, repeat, think about this keep rolling, right? You have at every time point you have three different states. Okay, second time point you also have three different states. Okay, if you're at the third time point you're in one of the n states, one of them say state 2. Okay, what's the probability of being state 2? It could be this line, right? This line, so you sum up all those possible ways of getting from time 1 state 1, time 2 state 2, time 1 state 3, time 2 state 1, time 2 state 2, time 2 state 3, and then finally time 3 and state 2, where sum up all of those probability in the transition probability, sum it up so that you get the probability that in time t you're in m state. Okay, so we need to account for all possible those probability paths. Okay, and each of them account for a certain probability. You need to sum up all of them to give you the total probability that finally you're in a particular state at time t. Okay, just keep this in mind. So we can write them, of course, as a matrix notation. Okay, P of t, okay, equals to a t minus 1 multiplied by initial state probability, where P of t equals the probability of your in each of this matrix, and A is the transition matrix. Okay, the two example cases we've done last time, I'll go through them quickly, and then we'll move into the other questions. One is the observable state. That's your games on intuition. If you assume you have a first order Markov model, the observation is observable, or sometimes we call it deterministic. Okay, so the state and observation are equal to each other. Okay, there's no randomness, there's no probability associated with them. Okay, for example, here you assume you can observe the state, and there's a direct observable relationship between the state and a model. So state and its corresponding output. Say, for example, in this case, when you're in state one, you always observe rate deterministic, okay, nothing hidden here. So when you observe this, you know you're in state one. Okay, there's no probability that you're in state, there's probability of point A in raining and so on and so forth. Okay, so we call this kind of an observable Markov model. So in this case, the weather metrics, okay, state one is raining, state two is cloudy, state two is sunny. Somebody gives you this transitional matrix. So when you're in rainy day, the next day you're still in rainy day, it's about 40% of chance, right? Or the next day jumps to cloudy day, it's about 30% of chance. The next day it goes to sunny day, is about 30% chance, so on and so forth. Okay, so sum this up, it go all adds up to one. So somebody gives you the transition matrix, somebody gives you this transition matrix. This is state and observation correspondence. You can ask various questions around this Markov, first order Markov weather model. What's the probability of particular weather sequence or weather patterns? Sunny, rainy, cloudy, given this particular weather model. Right, so again, so you want the P of this particular observation given model, right, correspond to the state sequence, right? Sunny, rainy, cloudy. We know sunny is 3, sunny is 3, rainy is 1, cloudy is 2. So eventually what you're trying to find out is the probability of this particular state sequence. Okay, because there's no probability between sunny versus state. So when you observe sunny, you know this is state 3. So eventually what you need to find is this probability of observation essentially becomes the probability of state sequence, okay, in a first order Markov observable model. So again, we try to problem finding the probability of this set of observation to essentially find the probability of a state sequence. Okay, so the probability of a state sequence 3, 3, 3, 1, 2 given model, right? This is under a particular model parameter with joint distribution of state 3, 3, 3, 1, 2. Okay. Now, because we know it's first order Markov process, so this joint probability factors into conditional probability, but only conditional on one previous time point. Okay, so there's a first order Markov assumption we build in to these kind of Markov system. So probability of 3, probability of 3 given 3, probability of 3 given 3. Otherwise, this one should be probability of 3 given 3 and 3. Right? Because the first order Markov assumption is only probability of 3 given 3. Also, the probability of 1 given 3 and probability 2 given 1. And this is initial state probability. These are just transition probability when you're in state 3 going to state 3. When you're in state 3 going to state 3. When you're in state 3 going to state 1. When you're in state 1 going to state 2. We just need to read off from the transition matrix table and then just plug it in. And you can multiply it to it and get it. That's just A33, that's just A31, that's just A12. Now, if you assume our starting weather was always sunny, so pi 3 equals to 1, then your answer can actually get an exact number called 0.0192, basically 2%. Okay, see this kind of sequence under this particular weather model is 2% of the probability. Okay, as a second question, okay, can ask various kind of probability question around this kind of modeling. Given that the system was in state I, what's the probability you remain in that particular state for exactly D days, right? So your observational sequence is this, right? You're in state I, okay, what's the probability you remain in that state for exactly D days? So it has to be in that state I for D times, and then next time at D plus 1 it jumps, okay, to some other state other than the state I. So observational is basically what D days and D plus 1 is something that goes into the J state that does not equal to I state. Okay, so the probability of the observation given model, and also you need to know at Q1, and it has to be starting at the I state, because P of O Q1 equals I given a model, by P of Qi equals to I, and this is pi I. What's the probability of observation of given observation n Q1 equals to I, and you start, this joint probability becomes a factorized. So factorized into a conditional probability that follows first order Markov. Pi I times AII, right? Because you need to stay in the I state. Okay, this is the first state. This is the D minus 1 state. They all need to be stay in the I state. Okay, so this 2 multiplies. That means the system already in the state I for D days. Now the next state is going to jump. Okay, it's going to jump up to other state aside from the I state. So we need to transition from other to other state. Okay, what's that probability? It's basically the probability of you not being in the same state. Okay, because probability sums to one. So the probability of you jumping to other state equals to probability of not staying in the same state. Okay, so that's 1 minus A, I. Okay, so then you multiply all these things. You get this number A, I, T minus 1 minus A, I. Okay, so we call this thing is the probability distribution of duration D in state I. So for any particular state I, okay, there's a probability on how long it's going to stay in that particular state. Okay, and look at this number, right? As D goes, okay, as get these larger, this number gets smaller, right? So eventually, right, it's always called exponentially decaying. So you cannot always stay in the same state under the first order Markov assumption. Okay, at some point it's going to jump out. Okay, because that probability will be too small. Okay, so it's the probability of you staying in a particular state as D goes or time goes, that's going to have an exponential decay function. Okay, when we're under the first order Markov process. All right, that's observable, okay, where the observation that you see directly linked to the state that you see, okay. For Peter Markov model, there's basically add additional probabilistic layer, which is the observation is a probabilistic condition on the state, okay. So it doesn't have a deterministic relationship to the state number. So the states are now not directly observable. That's why we call them hidden, okay, Markov model. You don't see exactly what the states are. You see a probabilistic function output of that state, okay, which are the features. So that's kind of what we, as in terms of speech sort of technology, that's how we abstract the speech production process, right? There's a hidden movement, okay, that your lung pushes out air, it starts to have a sequence of generating through whatever articulator that you have. Finally, you open up your mouth, okay, sound comes up, okay. So there's some hidden sequence of events that are happening with the articulator that eventually generate the speech sound that we see and measure. Okay, so the thing that we can see and measure are actually this the waveform or the MFCC features that we extract. Okay, we assume it's being generated as a probabilistic function of some hidden state. Okay, some system that's being used to generate all these things. So the analogy really is along that route, but mathematically what that really means is just the output things that you see, whether that's feature or value or something, is probabilistically conditioning on a state. Okay, so you don't exactly know what a state is, even though you observe the observation, but you know there's a probabilistic relationship between the two, so you can use it to kind of somewhat infer the state, or even not to infer state, just say, okay, there's some generation process that happening within a hidden state. So again, we did a simple cases, right? Okay. So for the Markov model, the observation is a probabilistic or random function of the state. Okay. You need a model that has output relationships and transition are both probabilistic. Underlying state sequence is not directly observable, so we call them hidden. It's only observable through another random process. It's only observable through a probabilistic function. Okay, you don't really know what that state exactly is, but you know if you're in that particular state, that know probabilistically it's going to generate some feature values or some values at C. Call it hidden Markov model. So we need the state transition probability like we do with the model. You need this state transition probability to tell you the first order system sort of dynamics. Okay. So the output emitted once you're in a particular state, right? The system has this kind of state 1, 2, 3, right? It's a discrete time system, discrete state, discrete time. It happens every time you're in one of the end state. Okay. It's just that once you're in a particular state, the output can probably function of the state. Okay. That's what really hidden Markov model is. The state is hidden to you. The system will go as is, right? System 1, state 1, click, go into another state, click for another state. That kind clicks changes depending on the state transition. Okay, when you're at a particular state, the feature you see can probabilistic condition on the particular state. So we did try a simple example. There are very many variants of this. It's like probabilistic probability course, right? These are very easy exam questions. There's so many ways you can massage this question. It's about different questions, but just understand the major concept behind this. Right? You're in a room, your friend is behind the screen with two different coin. Okay, coin one and coin two. Okay, you call it different state, right? He tosses the coin at time. You can choose between coin one and coin two alternatively. Okay, you don't know when he switches between coin one and two. You don't really know which coin he uses to toss. You don't know which type of coin he uses, whether it's a biased coin or a fair coin. Okay, you only observe the outcome of the coin toss, right? Some probabilistic functions of the state transition, right? So a state is a coin, right? There's some state transition. Okay, sometimes you switch between coin one and coin two. And every time you use one particular coin, you don't see the coin. You see the outcome of that coin, okay, which is head or tail, which is a probabilistic function of that coin toss. So just imagine this process is very similar to we see in speech. Okay, so if you know certain probability, okay, you know the probability of this coin switching. So the state transition probability is 0.25. Okay, of course, when we talk about Markov model learning, we don't know this, so we have to estimate this. We'll talk about how we estimate this later, but let's assume in this case, you know the coin switching is 0.25. You also do know, okay, there are two type of coin. Okay, so these kind of two states, okay, different states that has its own variation. So one of them has to be a fair coin. So when we say fair coin, now when it tells you it's a fair coin, okay, it tells you a probabilistic function of the output depending on the state, right? Because it's a fair coin. When I see head, that's probably 15%. If I see tail, it's 50%. We know another one is unfair coin. Okay, it could be, okay, head bias. That means the probabilistic function of the output, depending on whether you're in that particular state, if it's head tail, it's 75%. If it's tail bias, then tail will be 75%. Okay, so this kind of state condition, the probabilistic function. Of course, in reality, right, for hidden Markov model for speech processing, we don't know those parameters. These are we can estimate this, but just given this question, we assume we do know. Okay, so you know the probabilistic functions of the state. Okay, when it is in a particular state, then you know that function of the observation given the state is 75%. If it's head bias or it's tail bias, 75%. You know, it always starts with the unfair coin. Okay, again, you know the initial state probability. Okay, again, in reality, you don't know, you need to estimate this. Okay, but just assume you know. I always know that it starts with the unfair coin as a toss. Now you have this problem set up, right? And we talk about this. If the following observation was given, okay, your friend throws a coin and twice give you, just say, okay, I'll tell you my observation is head tail. Okay. Now, can we actually tell which type of unfair coin was used? Right? So you have hidden Markov model of two kinds, right? Your friend is your hidden Markov model, right? He's generating observation head and tail. Okay. Your friend can have two different kind. One is with a head bias unfair coin, or another one is he's throwing with a tail bias unfair coin. These two will give you different outcome. We just look at the observation we see and compute against one of this model and see which is more likely, and you can tell. Okay, if this model is more likely, it's probably coming from a head bias. Okay, if the other model is more likely, it's coming from a tail bias. But we just need to compute the probability of the observation given model. So that's all we need to do because of this problem. So how do we compute the probability of observation model? Let's make sure we have all the parameters in space, right? So two coins, two states, n equals 2. State transition probability is 0.75, 0.25, 0.25, 0.75. Okay, because there's 35% chance you stay in the same state, right? 25% chance you switch, meaning you switch to another coin. We know you always start with a fair coin. So if you assume the first state is always a fair coin, second state is an unfair coin, your initial state probability is 0 and 1. Okay, again, this parameter also set in the question review. The output probability is the only thing that will change, right? You have two kinds. Okay, first model is a head bias coin. So when you are in state, you're in state 1, fair coin, seeing a head 50%. In state 1, seeing a tail 50%. If you're in model 1 case, When you're in state two, unfair coin seeing the head, that's 75% because it's a head bias. You're in state two, meaning the unfair coin seeing a tail, that's 25%. And it's one kind of model. So you can write that as BJOK, right? So depending on observation and which state you are. Now, the second model, right? If it's a tail bias coin, right? The same thing, the fair coin still remains the same. The only thing changes the unfair coin will become the tail bias, right? Then you're in unfair coin seeing ahead because this is a model of tail bias coin has become 25%. Okay. So again, PO2. So when you're in state two, okay, seeing a tail under this particular model, okay, because this is a tail bias model, then you have 75% here. Okay, now you have two different models. All the rest of parameters are being known. So what you need to do is to compute P of O given lambda 1, which is a head bias coin, okay, head bias sort of hidden Markov model, for P of O given lambda 2, a tail bias hidden Markov model. Okay, so we have these two different models, right? Two different central parameters. We want to look at the observation, which is head tail. Look at whether it's more likely coming from this or more likely coming from that. Okay, so what we need is compute this probability of observation, right? Given lambda 1. Okay. So how to compute this probability of observation, right? It sees head and tail, right? Initial state, right? We have an initial state. Okay. Sum of all the possible ways that you can be in one of the initial state, right? When you're in that particular state, seeing the first observation, like that probability. So initial state probability multiplied by when you're in that particular state, multiplied by the observation that you seeing that particular observation, this probability then transiting from I state to J state as going to the next time, right? So you have the head and tail. So at the second time, BJLT. So when at the second time you're in state one, okay, seeing the tail. Some also, and also the other one is again, J go from 1 to 2, so it can be different states. So the first fair or unfair both seeing a tail, that probability is sum it up. So you get this total probability of you seeing the observation given this particular model. Again, repeat. We need to find the total observation of the O given lambda 1. So we need to find all possible cases, okay, that this particular hidden Markov model will generate head and tail, right? So all possible ways that this hidden Markov model can generate head or tail is first, you start in one of the end state. When you're in any one of the end state, you're seeing a head as your first observation. Now, in any one of those states, you transit to any one of the J state. And in any one of the J state, you see a tail at the second step. Sum of all of those things will be the total probability that this model is likely to generate the observation that you see given this model. Right, so you have all these parameters. You just need to, plug in the numbers. Eventually get 15 over 64. Moving on to the second model, right? Again, you want to find a probability of observation that could generate from lambda 2 and repeat, see a head and tail. Okay, you have another set of model, hidden Markov model lambda 2. You want to look at all possible ways. Okay. That hidden Markov model can generate these head tails, and some of those probability become the total probability that this model can generate the observation. It's not asking you one particular way of generating, it's asking you what's the total probability that this model can generate that observation. So you don't really care whether your friend tosses fair or unfair. Okay, you don't actually need to know the state sequence. All you need to know is out of all the possible state sequence, is it more likely it's coming from this particular model of tail bias or that particular model of head bias, right? So you sum up all the probability that this particular model can generate this observation. Okay, so you can compute all those things, it becomes 11 over 64. So sequence, right? Head and head tail most likely come from model 1. Okay. The state sequence, the actual process that your friend uses to toss a coin, you don't know. It's still hidden to you. Okay. But you now have a best guess, okay, that he uses the head bias coin in that process of throwing. Okay. So this probability of O given lambda will tell you, if he uses a head bias or a tail bias coin, out of all possible ways he can use those coins, this is the probability he's going to give me the observation of head tail. So I can look at which one is more likely. It doesn't tell you, okay, which coin exactly he uses, like first coin, then second coin, or second coin, or first coin. But we are able to compute the total probability of seeing the observation given this stochastic model. Okay. Later we'll tell you guys a particular way of finding the best state sequence, meaning what's the actual coin that he uses most likely, okay, to have generated the tail. Okay, maybe it's coin 1 and 2 or 1 and 1. You have to find a way to actually compute those things. But this only tells you it's most likely out of all the possible ways your friend can utilize that 2 coins in alternatively give you head tail, what's the probability of coming from this particular model or that particular model. Okay, but that already can help you do some answering, right? You can answer, okay, this you're using the head bias coin or using the tail bias coin, and you have an educated guess, okay, because this guess is based on probability, okay, this guess, this classification, okay, this recognition experiment is already done in the maximum, most probable sort of a detection kind of setup. Okay. So we'll go to the details of HMM's questions, okay, and we'll show a more in-depth discussion around HMM's. Okay, now, first one. So the 3 basic questions or 3 main questions about HMM. Given the observation sequence O01 all the way to OT, HMM lambda, basically the model has all these parameters. How do we compute probability of O given lambda? Okay, we know, sort of, okay, P of O given lambda is basically sum over all possible state sequences. Okay, when you're in that state sequence, times the probability of those state sequences, and when you're in those state sequences, then what's the observation that you see, right? So as long as we have these 2 things, sum of all possible cases, we are able to compute P of O given lambda. Okay, we'll quickly see these things become intractable when your T is very long. Okay, you need to find an efficient way of computing instead for just blindly summing up all these state transitions. We'll introduce a method later. The second one, right? Second question: given the observational sequence and a model, right? Given HMM, given an observational sequence, how do we choose a state sequence? Okay, which is unknown to use a Q1 of the QT that best matches the observations. Okay, that best describes, right? In the coin tossing cases, right? It's not just knowing which head is your friend using head bias or tail bias. Can we actually find a way to tell me, okay, he actually throw fair coin and unfair coin? Okay, so that sequence, can we find a way to actually identify that sequence? Okay, that best matches the observation we see. We'll also talk about methodology to do that. Okay, last one is called learning, right? Because Peter-Markov model only things are exercise in Peter-Markov model. Once you have parameter, you can ask these questions. But what if you don't have the parameter? How do we estimate those parameters? Okay, from data. Okay, so that's we'll talk about this mainly in a speech recognition context for H-phony acoustic modeling and so on. So we do have a way to try to estimate all these parameters. It's going to be based on somewhat of a maximum likelihood estimation kind of approach, and because there are some issues around this maximum likelihood function of this hidden model, we cannot directly solve it. Okay, it's not just simply taking derivative and set equal 0. We have to do iterate the approximate solution. So we'll talk about a particular algorithm called EM algorithm that tries to solve the estimation and learning problem. Okay. So these 3 basic questions we'll go through one by one. Okay, the first one. Given the observational sequence, okay, HMM, how do we compute P of O lambda? Efficiently, that's a key word here. Okay, but first I'll go why. Okay, this P of O given lambda, okay, probability of the observational sequence of a model gives us a notion how well a particular model matches an observational sequence. Sometimes we call it scoring. Okay, you can score your sequence against a particular model. How likely it is coming from that particular model. Okay, so because you're computing the probability of the sequence of observation for the model, right? So you can compute for all the models. You can compute how likely it is coming from a particular model. We call that scoring, knowledge-wise. So if you have multiple competing models, you can compute P of O given lambda for all different models and provides a way to choose a model that best matches the observation you see. So you have multiple models, you have one single observational sequence. You can look at which one is more likely. So you could score against each of the model and which one gives you the largest probability is probably coming from that particular model. Question 2, given an observational sequence in a model, how do we choose the state sequence that best matches the observation? Okay. In general, there's no correct or even the unique state sequences. We usually need to find some optimality criterion to choose a state sequence. Okay. So because things are hidden, okay, of course, the observation is already a random function of this function of the state, and state sequence is never observed. So how do we actually choose a state sequence? So it's very difficult to say there's a correct answer. Okay, there's a good answer under a particular criterion. Okay, so you choose a particular criterion and say, okay, under that particular criterion, what would be the best state sequence that was originally hidden to me now become observable to me? I can compute it. Okay, so trying to find that. Okay, is useful for continuous recognition because the speech recognition is a concatenation of phonemes. Okay, you don't just score against A and then you're done. Done, right? Because these are actual strings of words. Okay, it becomes a strings of phonemes, strings of acoustic models. So you want to score sort of a decode across different phonemes and stuff like that. So you need to find a good sort of sequence to be decoded. Okay, so we'll talk about this also later. Okay, the third question, right? Given a model, HMM model has only set parameters. How do we estimate model parameter represent a particular specific class or specific model? In other words, how do you use data, okay, to derive from each class to train your HMM? Okay, so previous two classes are basically how to exercise the HMM. Once you have parameter, you can use it to answer those questions. Here you say, okay, I have a model, I only know the parameter, I don't know the values of the parameters. Okay, how do I get the values of those parameters? You can collect a bunch of data for each of the class, then you can train the system to be able to get you the values of those parameters you can use to compute the probability of observation, or you can try to compute some state sequences. That's question 1 or 2. Okay, so after training, people call it learning or estimation. You can use the train or learn model for recognition. Okay, so that's the third question. I'll continue the first question. Calculate the probability of O given lambda when O is a sequence of observation, right? O is vector, right? O1 can be MFCC, non-MFCC, all the way to OT, right? It's the ending frame of a sequence, OT, okay, if your model has n states, okay, so you have T frames, right? T time, okay. The model has n states, okay. So total number of possible state sequence, that's n to the T power. Okay, so again, think about you have say 3 states, 3 times, then you have 3 times 3 possible state sequence, state path across this matrix of 3 by 3, right? So now think about you have n state, you have t times. Okay, let's not make it very lengthy. Just okay, we'll compute now. But no, for a given particular state sequence, like Q1 to Qp, the probability of observation given that particular state sequence of a model, right? P of O given a particular state in a model, is just the probability of T from 1 to T, probability of OT given that actual state, okay, QT multiplied, and under that different model, under that model. So the observation of statistical independent given state. So if I know in that particular state, I will also see the observation. So probability of O given Q and lambda is, if I know the state, then I can directly compute the probability, right? B of Q1 O1, B of Q2 O2, B of QT OT. So the probability of this particular state sequence, right? P of Q equals lambda is initial state, and you're in Q1. Q1 go to Q2, Q2 go to Q3, all the way to Qt minus 1 go to Qt. So this P of O given lambda is essentially the sum of the joint probability P of O Q evaluated all possible sequences, right? So the answer is right, P of O given lambda, sum of all Q state sequences of this joint probability P of O Q, P of Q given lambda. Again, in the plain words, right? Still we know a particular state sequence, okay? it's not here, it's known to you, okay, that's known to you. That particular state sequence, under that particular state sequence, I know the observation, because in that particular state sequence, I can compute the probability of observation when you're in that state. This gives you the probability of that state sequence itself, okay. So for one particular state sequence, okay, you multiply the observation, right, probability states sequences multiplied by the that particular state sequence probability, and you sum over all possible state sequence that exists, okay, within this n by t kind of a combination. Okay. So if we compute this probability directly, okay, it's roughly close to n2t times n to the t power. This is the problem, okay, because there's so many possible sequences to enumerate through, okay, because there's state sequence, one here, one here, one here, two here, two here, two here, another one here, another one here, another one here. So all these things is a path. A path has a state sequence probability. Along that path has a probability is a probability observation probability, and you sum up all possible state sequences out of this model to get you the full probability. So the problem is this n to the t power. So let's imagine a very simple case. Just say you have 5 states, okay. T not very long, okay, 100, okay, say, 15, 20 millisecond a step, right? Think about it. MFCC, we computed with 30 to 40 millisecond and 50% overlap. So that's about 20 millisecond, 20 millisecond that's a step. 100 of them is about 2 seconds or so, okay. That's not very long of a speech, okay. So basically n equals to 5, t equals 100, okay. So you have then about n to the 100th power of that state sequence you need to evaluate through. Okay, so again, that's not possible. Okay, so you cannot compute, you cannot score the probability of the observation given this model efficiently. Okay, because there's not enough time to go through all the possible state sequences. So the problem here is what happened. Okay, the issue here is we are directly summing all possible state sequences from the beginning to the end. Okay, what that means is you go through each state sequence going from t from 1 to t. Say 2, okay, the second state sequence going from t 1 to 2. Okay, so if you think about, right, just 3 by 3, okay, going from 1 over here, another one over here, another one over here, and then 2 goes from here to here. You see, at this point, there actually redundant calculation has happened. Because not every state sequence have own distinct pattern. Okay, there is some part of the net overlap. Okay, but you treat every state independently and you sum over all of them. Okay, that becomes very difficult because you have to go through all of the possible state transitions from T1 to T capital T. Okay, so that makes the computation complexity very, very high. Okay, very, very difficult to do. Okay, so we'll introduce a efficient computation method called a forward algorithm. Okay, so let's try to take away the redundant calculations that happen. Okay, when we actually enumerate all the possible state sequences through. Okay, let's define first a variable at time t, alpha ti. Okay, this is a probability of the observational sequence up to the point also t. Okay, lowercase t, not capital T. Okay, so alpha ti equals probability of O1 all the way to OT, and you're in time tqi equals to the I state. So alpha ti equals the partial probability of observation up to the point t, and where you're in point t, the state is I. Let's define that probability. Okay, so there's a joint probability of partial observational sequence until time t, not the end. Okay, and the state at time t is in this case should be I. So it's given the model. Okay. So how do we compute this iteratively? Okay, do a simple induction. Okay, at time equals 1, okay, the system starts. Okay, this is A1I, right? So that's a partial observation of the first time observation, and Q1 equals to I, given this model. Okay, what's this probability? This is just pi I, right? Initial state probability. When you're in that state I, you see the observation O1. We write them as BIO1, right? So you're in state I, seeing O1, multiplied by your initial state probability of I. Okay. let's do some calculation. Assume t equals t plus 1. Okay, so alpha t plus 1 equal alpha t plus 1 of j equals what? Equals to sum of the probability of alpha ti. Okay, because this account for all the probability up to the time t. Okay, you're in state I at the previous time point. Okay, all the I go to j. Okay, sum up all the I go to j. Okay, now you're in this time bj of t plus 1. Okay, right, and continue at the end, right? How do we compute the total probability? Total probability of P of all given lambda equals essentially just sum over the final step. This forward variable alpha evaluated to the point t, okay, capital T, I state, sum up all the I state, and you get the total probability. You see this iterative, okay, because this alpha t of I is a partial observation, probability of partial observation up to time t, and you're in state qt plus 1, okay. So up to state, so you can see alpha 2 of I, right? You can say alpha 2 of I equals alpha 1 of I times alpha 1. Okay, go to all the alpha I to the j state in the second time step. Okay, all that transition probably sum it up. Okay, and multiply by your in the second time step. Okay, you're in the observation particular j's operation. Okay, so because that alpha 1 because this alpha t includes all the past information about the partial observation up to time t. Okay, so when you move on the next time step, what you only need to do is to multiply all possible ways I could go to the next time steps in a particular state. Okay, and multiply by when you're in that particular state of observation. Again, repeat, right? So previously you're saying, okay, I'm going through all these paths. Every path I have a state sequence. Every state sequence has a output probability. I sum up all those things one by one. Okay, that takes very long because they're n to the tth power possible state sequence you can generate from the n times m state t times step system. Okay, now we're saying let's define a forward variable called alpha t of I that accounts for the probability all the way up to this particular point, the partial observation up to this point, and you're in this particular state. Okay. So when you move on to the next time, what you need to do is recompute these alpha t variables for this t plus 1, the I state. Basically, okay, I'm now in I state. Okay, I come from one of the n state previously. I just need to sum up all possible ways I could come from the previous state to this state. And when you're in this state, in the probability associated with this particular state. And basically, you just time rows, and then you compute this alpha t, time rows, and compute this alpha t. So you don't get redundant calculation. Every step, you only need to calculate once of how you actually come from the previous time point. Sum up all those probability for each of the states. Sum up all those probability for each of the state, and then you just as time row. So you're not going horizontal one by one and look through all the state sequence. You're redefining a variable that actually captures all the probability up to this particular time t. And then you do it iteratively, inductively to compute this alpha t. Okay, so basically makes things much faster. Let's do a little example explanation here. Okay, step 2, right? State j can be reached at time t plus 1 from n possible state. Okay, from t. So at of I is a joint probability of observing O1 to OT and state I at time t. So alpha t I times aij is the joint probability of this particular event is observed, and the state j is reaches through state I at time t plus 1, right? So again, this is that's already a couple of joint probability of all observation up to time t, and you're in state I. Now you're moving into state j, right? Because you multiply by that transition probability. And sum up all these i's. Okay. So basically that means reaching state j time t plus 1 from all possible states from I from 1 to n at time t with all previous partial observation. So all the probability that you need, okay, account from all past history, okay, is going to be captured in this probability. Okay, so everything up to this point, at of I multiplied by aij, so you know the probability of me going to the j state. I look at all possible ways at my particular time to go to the j state, and you sum up. That will be the total probability I could reach that particular state up to that point. And accounting for all the partial observation that already happened in the past. This is four variables. Now, once you're in state J at time t plus 1, it's just this, right? A alpha t plus 1j, is that this? And now you are moving into t plus 1 time when you're in state J. Now you just need to multiply in that particular time index in J state, the observation given to you, give it the observation. Then you have this alpha t plus 1 alpha j. Now just repeat for J for 1 to n, and then T for from T all the way move to T minus 1, right? So you just repeatedly do this thing again. Every time rows, all the state, right? All the state has one of these values. Alpha T minus 1 of J. J can go from 1 to n different states. Time ticks, can recompute this probability. You have another set of alpha T plus 2. J go from 1 to n, each one has a value. Move on again, then you again, each time that you can repeat computing this until you roll to the end of the sentence or end of the sequence. Okay, after repeating this, you get to the final frame of P capital P I. Okay, P of O given lambda essentially is just sum over I from 1 to n alpha, this capital I, right? So let's read off what that exactly is, right? That's the joint probability of all and all possible state values with all company partial observation. So basically you enumerate through all possible cases already. So it gives you the final probability of observation given the lambda. So previously what we did is look at each possible state sequence. That possible state sequence has a state transition probability. Under that state sequences, it has this observation probability. We sum up each state sequence one at a time, and you try to find all possible state sequences, sum up all of them to get your P of O given lambda. Okay, the problem again is the n to the t power. Okay, that number of state sequences has to occur. That summation happen for all of those things. That's too many. So we break down the problem. Instead of doing that, we say, okay, we define new variables. That variable is a probability. We can compute it iteratively across time. Okay, it'll always account for all possible probability that needed to compute the probability you're seeing at this particular point in time in the J state. That's all it needs. Okay, that probably accounts for that. Okay, so when you move on to the next time, you just need to look at how it's going to move to the next time step. Okay, and then repeat for all J, and then next time repeat for all J, and then finally at the end. You just sum up all those things, because once you sum up all those things, it's equal to the summations of all the state sequence path. You actually just sum it together. Okay, so the number of calculation is just n squared t, much fewer computation, are really fast now. Okay, so and then it gives you the exact answer of the P of O given lambda. This is exact answer. There's no approximation. It gives you the exact number, the same as if you were to enumerate all the possible state sequences. Okay, again, really the basic idea, right, is each of the n possible state at t plus 1 can only be reached only from one of the previous n state at time t. Right? So if you want to compute some probabilities out of the entire thing, we just need to slowly roll over this. Right? At t minus 1, this accounts for all the probability up to t minus 1, and I'm in state 1. This is and then look through all the states. So this is the probability I'm in t, in t minus, oh, sorry, it should be t minus, it should be t plus 1, right? So at time t, the probability account for all partial observation up to time t when you're in n. Okay. Now time clock ticks. Okay, I roll into the next frame. Okay, I find a new set of forward variable, because this variable tells you at time t plus 1 in J. Okay, J can only go from one of the n previous state here. So each one of these can go here with a probability of the transition probability A1J, A2J, A3J, ANJ, right? So that's the only probability that can come to here. Once you're in here, you multiply by the omission, the output probability. Now that you're in J state, okay, there's a probability. You multiply that, you give you this number. Repeat for all of these things, and you move on. Okay, so every of this account for everything. Now, assuming at the end, this is your n. Okay, this account for all the probability up to the n partial observation up to this point, and at the ending point, you are in state 1. All right. This is the probability that account for all possible observation in the past and the ending state is state two. To the this one up to the probability of the ending state is end state, count for all partial observations. So we just sum this all up. It gives you the final total probability of all the things you could possibly see in this model. Okay, so becomes a very fast computation, and these variables we call them forward variable because you compute forward in time. Okay, every time you compute it, okay, you move on. Every time you compute it, you move on. Every time you compute it, you move on. Okay. Now there's a forward and there's a backward. Okay, so you can do it from the beginning to the end. You can also do it from the end backward to the beginning. Okay, so with a similar logic, we can define a backward variable. Okay, b of t of I equals to the partial observation of ot plus 1 all the way to n ot, given that qt equals to I and this particular model. So the probability of observational sequence ot plus 1 to the ending point, okay, ot, given that the state time now is I, okay. So we can initialize this b of t of I equals to 1 for I from 1 to n. Okay, then by induction, we can say, okay, bt of I equals to sum, again, all possible ways. We got b, beta, bt plus 1j. You're now in b of the j state. Okay, ot plus 1, a goes from all the j to all the I. You sum up all the possible j's, you get to bt of I. Okay, again, rolling backward in time. Here it is rolling forward. So we get the probability of all the observation up to time t minus 1, and now you're in that particular time and then in that particular state. Here's the probability of you look forward in time, say account for all the probability from the t plus 1 all the way to t, given that qt equals I and lambda. Okay, and that termination is just sum up. Okay, I from 1 to n, the initial state probability bi or 1, okay, b1i. Multiply all these things and sum it up, get the final total probability. This number will be exactly the same number as the forward variable you got at the end point. Okay, this will be the same number. So basically, they are exact computation. You just define the forward variable and backward variable. Okay, again, some interpretation, right? In order to have b in state I at time t to account for the observational sequence of forward looking, right, from t plus 1 onward, need to consider all possible state j at time t plus 1, accounting for transition from I to j, call it probability of aij. Then you account for partial observation at time t plus 1, so that's why you need to compute for bj o t plus 1 at state j. Okay. Then you count for all the remaining observation sequence from the state j within the bet plus 1j. So basically the idea is very similar still, because you can only move one step at a time, because your transition probably only happens in the first order Markov process sense. Okay, so you can only go from this state to next state, and it only depends on one period state. So by that particular first order Markov assumption, you can design in this forward variable and backward variable to help it efficiently compute the probability of observational sequence under this kind of Markov transition sequences. So there are two efficient methods in computing p of O given lambda, right? So originally it was trying to evaluate this for all state sequence, okay, p of OQ, right? If you know Q, okay, I know all the observation, okay. That probability multiplied by the probability of actually that particular state sequence. Okay, we sum up all possible state sequence, then get this. Okay, now we know the problem is this is summing up of the whole state sequence. If you do it from T1 to T and all together, every time you do it that way, it had too many state sequences you need to compute. So the two methods that we introduced here define a forward variable and a backward variable. Okay, so that you can compute efficiently. Okay, forwarding, okay, time rows such that forward variable accounts for all partial observation and back. Backward variables is as time roll back in time, okay, it accounts for all partial observation all the way to the future to the end. Okay, and these two things can all the way roll to the end, then they'll give you the exact same answer of the p of the observation given this lambda. And this thing we call it the forward algorithm or the backward algorithm. Okay, you define it as forward variable, backward variable. Okay, I think given time, I'll do a little starting of the point problem 2, but we'll take a break. Okay, that things sinking a little bit. Okay, we'll come back to problem 2 to really solve it. But this is problem 1, right? Trying to efficiently solve probability of observation given a model. The problem 2 is the finding the optimal state sequence. Okay, I want to set up the problem. We'll try to solve it next time. Okay. So how to find an optimal state sequence? Okay. What does it mean to be optimal? Okay, we can first look at a simple case. Okay. First, okay, if we try we call it local computing. Okay, every per time index using the forward or backward variable. Say you want to choose state Q and time T, which are individually most likely to happen, okay, in a time T, right? So if you remember, in the beginning of the class, we are able to, given a Hindenburg model, we can compute the probability of Qt equals I, right? So we know how do we actually compute at time T, your state variables is in I state. Okay, we can look at that for time T for all the state, okay, and pick one as the largest, right? And move on to the next time and say, okay, at Qt plus 1, look at across all the state. Look at which probability is largest. Okay, so we call this computing locally. So if at every time index, okay, you can compute which probability, which state has the largest probability and report that, okay, would that be the best description, okay, about the best optimal state sequences? Okay, so that's one sort of intuitive way of thinking about that, right? So we have P of O given lambda we can compute. We have this Hindenburg model. We know we can compute for each of the time, for each of the I, can get the probability of Qt equals to I. Okay, now we just look through all the I's and look through all the times and which one is the largest value and just connect them. And that will be the one possible with the best state sequence. Okay, so we'll see that as actually an issue. We can't really do that, but let's just set up the problem first. Okay, so suppose we can do that. Suppose we're going to do it that way. So it means the time is relevant, not trying to look for the best possible state sequence, just look at a particular time, what is the best state in. That's one possible way of doing things. Right? Another possible way of doing things, right, is this, right? For all state sequence here, right? Think about this setup, right? For all state sequence, for each of the state sequence, I have a probability. You sum up all of them, right? That means for each of the state sequence, you actually have a probability where you actually sum it up. So if you just store all of those probability, look at the largest of them. Okay, that's another way to do things, right? So yeah, because there's say for n to the t power state sequences. Okay, you just look through all them. You look at one of them, you compute one of the probability. Okay, look at another one, look at another probability. Okay, so you can say I can look at which of that state sequence give me the largest of that probability. That may be another way to solve this. Okay, but again, you can imagine that's also non-solvable because you cannot enumerate over n to the t power of things. Okay, and in this particular way, we're saying, okay, let's not look at the entire thing, but let's say, okay, look at individual locally. Okay, what's the probability of me being in a particular state? Okay, we're making the largest value in this case would be enough or not. Okay, so again, that's another way of looking at things. Okay, which not the right thing, but we'll start the problem. Okay, so let's define two variables, right? We already know forward variable and backward variable. Right? Forward variable alpha ti equals to a partial observation up to the point t. Your time in t, your state not given a model, right? Backward variable, okay, beta t of I, okay, partial observation of t plus 1 all the way to t all the way to any point given qt equals I and none. Okay. Let's define v t of I equals the probability of qt equals I given observation at lambda. So the probability of being in state I at time t given an entire sequence and observation, right? So vt equals I equals p of qt equals I given observation in this particular model. Okay, that equals to p of o qt equals I given lambda divided by p of o given lambda, right? So we know this here. Okay. So what's this p of o qt equals I given lambda? That can take this equals this is a sequence, right? So it's O1 to OT. So O1, O2, OT, QT equals I times OT plus 1 all the way to OT given lambda. Okay. Let's factor this joint distribution. Okay, that becomes P of O1, O2, OT, QT equals to I given lambda. Probably OT1, OT2, OT given QT equals I and lambda. Okay, these two multiply get you this. Okay, now if you look at this, this is a definition of forward variable. Okay, so that's alpha T of I. Okay. What's this? This is the definition of backward variable, which is beta T of I. Okay. So if you want to find the probability of OQT equals I given a lambda, right? Basically, you need to look at your forward variable and backward variable, compute it to the point T, and you get that I state. And these two multiply, it gets you this P of OQT equals to I, which is this number. Okay. So what's the P of O? Okay. Total observation probability given the model, right? Sum over I from 1 to n, P of OQT equals I, right? Because, let's account for all observation, okay? When in the particular time T, you're in state I. So you sum up all those things, it gets you everything, okay? So because it has account for the rest of the states and rest of the sequence of other time points, except for this T. So sum over all this T. So what's this? Okay, it's just sum from I from 1 to n, alpha Ti, beta Ti. Okay, because this we already know. This can be factored as forward variable multiplied by the backward variable. Okay. So we now have this Vt of I, which is the probability of you are in a particular state at time, state I at time t, given all the observation in this particular model, is this probability. Okay, we know this probability can be computed just for alpha Ti, beta Ti. Well, divided by sum of I from 1 to n alpha Ti, beta Ti. So forward variable times backward variable at a particular time, okay, looking at its state, these two multiply, divided by this two multiply, sum up all the states within that particular time frame. It gives you the probability of your QT, the variables are not in time t now is in the I state. Okay, so again, Vt of I, the A of, we know this forward variable accounts for O1 to OT. Beta variable accounts for OT to OT. So again, this is the probability we can compute using forward variable and backward variable. So we know Vt of I essentially is just a probability in a state I at time t given the observation, right? So one way we can think about this, trying to solve for best state sequence issue, is just say, okay, let's look at across all t, okay, within each one, find the largest I such that maximize Vt. Okay, right, let's try to find which is the largest value that the probability of being in state at that time t given this observation. Okay. All right, this is a one way of thinking about this, trying to solve for a best state sequence. But there's an issue here. Okay, there's a problem because this state sequence may not be valid. Okay, for example, you may find at qt equals I or qt plus 1 j. These two, when in time t, I is the most likely state. At time t plus 1, the j is the most likely state, but this transition may be 0. It's possible, right? Because the probability that we're computing is all possible ways it could reach here. Okay, so even though it is not possible to go from I to j, okay, but all possible ways it could reach here, this probability may be largest. So a state sequence going from I to j may not be the best one, okay, because it don't actually be possible to have I going to j. Okay, although individually at this state, at this time, I is the most likely state. At this time, j is the most likely state. Okay, so the logic will have to be very clear here. So when we try to say what's the best possible state sequence, okay, that explains the observation. Okay, you cannot just go about and finding individually, okay, through forward and backward variable individually at every time which is the most likely state. Okay, because this state transition can be can have a transition point that's 0 at the same time they're individually most likely state to happen. Okay, because again, repeat, if you imagine if you recall this this process, right? AT1J, right? Is sum up all the ATI of AIJ, right? So all possible ways me going from I to J. Okay, but maybe just I and J link is 0, but the rest of it has values. That makes this whole computation add up this thing, this mix multiplied by the backward variable may still be the largest value. So I is largest here, j is largest here, but aij may be 0. So if you're trying to find the best state sequence of this model and say, okay, at time t plus 1 is j, at time t is I, that's an invalid state sequence. So we have to make sure we account for this problem. Okay, the most likely state doesn't mean it could happen. Okay, it may also not happening with respect to this thing. Okay, so but at least I want to go through this part. Is also want to see this backward forward variables are quite important. Okay, in terms of this HMA computation because it helps you compute many of this partial probability very fast. Okay, because those are just time rolling in time or backward in time, and you're able to compute the probability you need across all the time index. But anyways, back to problem 2. We're trying to find a state sequence that best matches the observation that we see, but in a way that has to result in the valid state sequence. Okay, we'll talk about that today, next time. Okay, I think we should take a rest. We'll talk about Viterbi algorithm. Okay, it's a process of decoding. Okay, also inductive. Okay, again, through time, it's going to try to find what's the most likely state sequence, and that state sequence has to be valid. Okay, yeah, and it also guarantees, okay, the state sequence that it finds is going to be maximized. It's going to be maximized over all possible state sequences. So the state sequence that you find, the probability associated with that state sequence is going to be the largest among all state sequences. But do it in a way that's also time efficient. Okay, so you don't just compute for every state sequence and look at which one is largest, because that's too slow. So there n to the t power number of state sequences occur in any n to t in a Markov model generation process. So we need to make sure we have an efficient manner of computing what's the largest value of the state sequence and what are exactly those numbers of the states. And it cannot be done through individual slicing of the joint probability of the forward and backward variable. Okay, that's the thing I want to mention. We'll talk about this later. Okay, because this is quite important. Viterbi algorithm is used in many places, except from not just for speech recognition training HMM. Okay, it's basically a process of finding under noisy condition what's the most likely sequence. Okay, and usually it's discrete sequence. It's mostly a lot of times used in communication because communication is digital, sending digital bits, right? Those are zeros and ones. So it's trying to find at the receiving side what's the most likely zeros and ones that's being sent. When really I don't know what the 0 and 1 being sent at the sending side. Okay, so I want to decode the most probable state sequence so that I can repeat the communication at this side. So it's a process of decoding the best state sequence under noisy condition. And the noisy means a probabilistic function of the observation. So in this case, speech research also utilizes exactly the same concept in trying to find the best state sequence. Okay, so Viterbi decoding algorithm to find it's practically everywhere in your cell communication system right now. As a part of it has to use Viterbi algorithm in some form. Not in speech we use it to do speech recognition. 好，我们下次再往这边讲这个，我希望大家稍微想一下这个过程，稍微会有点复杂，但是一定要把它想清楚 ，OK， 因为后面就是我们会直接这个 build up 上去 ，OK， 所以这个 HMM 从刚才这个 random 的这个 sequence， 你要想，其实它有点像是一个 matrix，n to t 的一个 matrix，OK， 那 n 是 state t 的时间 ，OK， 那每一个程式选这一条路跟这一条，每一条路有一个 probability， 所以把它加总起来可以加总出所有的几率可能，对不对？那但是我不可能全部加总，因为每一条路要走完，每一条路都走太多条路，所以不太可能，所以它只好一步一步走，一步步走，它就自己发展出这个 forward 跟 backward。那你看第一个问题、第二个问题好像类似，但实物上还有不太一样的。第一个问题他讲说，只是我最后是要做 scoring，OK， 让我 scoring 过程中我设计了 forward 跟 backward variable， 所以让我比较好用时间轴去换取这个要走掉的路跑，就是一次走一步，但我走那一步的时候把全部可能把它加起来，所以就没有什么太大的问题，就是往下走，OK， 所以把 redundancy 透过每一步把东西加起来，再往下走，每步加起来往下走，那就变很快，不管那种 forward 和 backward。但我如果要回答一个问题是，我这串 LM 不是我这串的 HMM， 我转出来这个 state sequence 确实是哪一个 state sequence 哦，
你就不能够再说我一步步走，看那一步里面那个东西最可能是什么，因为它的最可能来自很多元的前面的可能，对，所以我这边最可能跟这边最可能中间这一可能性可能不存在，它可能不太可能从有可能 I 到 J 完全不存在，但是只是因为我 J 很有可能从各个地方来到这个 J 的几率很大而已，对，所以我变成我还是要去知道说我可以来自哪边，然后可以来自哪边是最大的可能性，然后我试图把这东西一步一步算出来。那这其实就 vector 和一个核心，然后下次会讲，所以它不能够单算这个当下最有可能，而是在算当下最有可能以及我最有可能来自哪里。OK， 然后把这东西记起来，我好像可以一直回推出我最终这整串 sequence 最好的最佳解这种 sequence 长是什么样子。OK， 这还有办法回答我讲的第 given equation what's the most likely sequence state。那这边在 continuous recognition 就会非常重要，因为你会有好几个 Peter Markov model 其实是串在一起。OK， 因为你的声音是一串一字连续下来，然后每个字是好几个 phoneme 串接在一起，可你其实是要去 decode 整个全部的东西，所以你可以讲后面的一个真的 ASR 其实非常非常复杂，你是好几个 model，OK， 同时间全部在 memory 开始做 decoding，OK， 那每一步都要记录这些什么 forward variable、backward variable，然后做这些东西去计算，然后我们到时候会再教一些 vector 可能也要做另外一个 variable 的计算，这全部都要记录在你的 memory 里面，OK， 所以是蛮大一个 decoding case， 但它让这整个 Peter Markov 当做一个 backbone 的 ASR， 它至少可以 work，OK， 至少可以跑得起来，动作也快，OK， 那这就是现在 modern ASR 的一个 backbone， 所以这个 H1 这边要蛮懂的 ，OK， 这个它的延伸后面说的 modern technology， 我觉得基本上都是 HMM 这个东西把它搞很清楚之后，它在这个框架下面做的其他的微调其他的调整，才让大家看到现在的所谓 modern 的 ASR 是什么样子。所以这边其实就是跟大家讲说，要因为后面会越来越快，有时候会 lost 掉那样，所以keep 这些in mind。OK， 好，我们先讲，我们下次再复习一下，再教 vector 比较。